Hello, my name is Sam John, and the topic that I'm going to present today is a low-power latch and flip-flop design. Here is the agenda for the presentation. First, I'll go over some basic concepts of latches and flip-flops and some differences between them. Then I'll go over why we need to implement low-power flip-flops and some equations related to power consumptions. Next, I'll talk about some research done to achieve low power flip-flops implementation. I'm going to show you 3 ways to reduce power reduction in flip-flops. Lastly, the conclusion. Let's first go over some concepts. Latch and flip-flops are basic components for storing data. They are used to build pipelines in the digital integrated circuits. There are 4 main types depending on the number of inputs and how states are changing. Those include SR, D, JK, and T types. Differences between latches and flip-flops are that the outputs of the latches are immediately affected by inputs, meaning that they are asynchronous. However, flip-flops are synchronous, and they are edge-triggered, referring that the output are changing only at the clock edges. Now you know the basic idea of latches and flip-flops. I'm going to explain why we need low-power flip-flops. Portable and wearable devices and Internet of Things, IoT, applications require low-powered integrated circuits. Sequential circuits such as flip-flops and latches are critical for pipelining, as I mentioned earlier. Also, they are important for synchronization and data storage, and they can be usually implemented using flip-flops. But timing elements using clock network are the most power-consuming blocks in VLSI system. They can take up to 70% of total power consumption. Also, as the CMOS technology process is getting smaller, there are more transistors integrated on the single IC, which causes more power dissipation. Thus, it is important to reduce power consumption of flip-flop to provide a longer battery life. I'm going to briefly go over some equations related to the power consumption. The first, instantaneous power, is expressed as the current times voltage. The equation 2 represents the average power in CMOS circuits, which is the probability of transition of power consuming activity times load capacitance times the voltage times the VDD time, clock frequency, plus the short circuit current times VDD plus the leakage current times VDD. And lastly, the power delay product, which is also known as PDP, is defined as the first term of the average power, which is bolded in equation 2, divided by the clock frequency. We now know why we're in need of low power flip-flops. I'm going to present how we can achieve this. The key to achieve low power application is to minimize the first term of the power average equation from the equation slide. Although there are many different ways to reduce power consumption in flip-flops, I'm going to present 3 researches that have designed low power flip-flops. The first one I'm going to show is a low power flip-flop logic style for high performance processors by Mehar and Mahapatra. The second one is a low power flip-flop design by eliminating redundancy, studied by Shin and Lee. Last one is a low power flip-flop design using virtual VDD scheme by Lin and some other researchers. First design to present is a low power flip-flop logic based on the basic dynamic flip-flop. Basic dynamic flip-flop in figure 1 is shown on the right. To briefly describe the system, X in the middle right here is precharged to VDD when the clock signal is 0. When the D, which is the data coming into the flip-flop, is 1, X becomes discharged, causing Q to set to 1. If D remains the same, then X gets discharged at every rising edge. One drawback of this basic dynamic flip-flop is that it has a large switching power, which is not ideal for low power application. Meher and Mahapatra propose a new design, which is based on the dynamic flip-flop presented in the previous slide. 3 transistors are added to the basic flip-flop. I have circled the new transistor added to the circuit. Starting from the top, M2 is a keeper PMOS. M6 acts as a discharging path. Lastly, M7 is a stack for the second path to keep the dynamic node. This proposed flip-flop becomes noise robust, which helps reducing leakage power consumption. The improvement of the proposed design compared to the basic flip-flop design is shown in this slide. As you can see in the figure 3 and the table 1, the proposed design, which is marked as 4 on the graph, shows the lowest power delay product compared to the basic flip-flop and 2 other commonly used flip-flops, which are static differential energy recovery flip-flop and single-ended conditional capturing energy recovery flip-flop. Also, the new design reduces 80% power consumption while increasing speed by 70 to 90%. It has also achieved the lowest power consumption for the data switching activity, less than 50% compared to other basic flip-flop designs. Now I'm going to present another low power flip-flop design by eliminating some redundancy in the circuits. Figure 4 shows the typical CMOS type flip-flop. There is a box with the question mark on the bottom of the figure. This is the component that is changed by Shin and Lee. The typical CMOS flip-flop uses 2 phase clocks, CK and CKB, or CK bar. CK bar is generated from the inverter, whose input, of course, is CK. In other words, for the typical flip-flop, the question mark in the figure is an inverter. This typical flip-flop causes extra power consumption due to the redundant CK bar transitions. One way to reduce power in this circuit is to eliminate redundant clock transitions when generating CKB. Figure 6 shows the CK and CKB waveforms. CKB1 is for the clock generation from the previous slide. As you can see, that CKB is changing regardless of the input data D. Shin and Lee proposed a new design called redundancy eliminated flip-flop, which is also called REFF, to reduce redundant clock transitions. Small swing clock flip-flop and 18T SPC circuits presented in the second column of the figure 5 have achieved elimination of redundant clock transitions while input D is 1. However, there is still a redundancy clock transitions happening when input D is low. The proposed design displayed in the third box of the figure 5 achieved the removal of the rest of the redundancy. Another way to further reduce power consumption is to eliminate redundant transistors. There are 2 methods to achieve this. First one is topological method, which merges topologically equivalent transistors shown in figure 7. Red X's are the ones that are removed from the circuit, which also helps avoiding contention conditions. Total of 3 transistors are removed from this method. Second method is logical method. It removes redundant transistors with inclusion relation as shown in the figure 8. With this method, 2 transistors are removed. After these 2 methods, 5 transistors are removed, giving us the REFF, which is a 25 transistor flip-flop. This slide shows the performance of the proposed redundancy eliminated flip-flop compared to the typical one. As you can see in the table 2, the new design passes functionality check conducted at 1 volt all the way down to 350 millivolts, which showed similar performance as transmission gate flip-flop and small swing clock flip-flop. Power reduction while generating clock is reduced by 70% compared to the transmission gate flip-flop. Lastly, when alpha, which is the activity ratio, is at 10%, it achieves 58% power reduction. Last way to achieve low power flip-flop design is using virtual VDD. The traditional flip-flop that Lin compared to were transmission gate flip-flops and AC flip-flop, which is SR latch-based flip-flop. The transmission gate flip-flop, which is one of the most widely used flip-flops, has some drawbacks. There is an excessive workload to the clock signal, which leads to the larger dynamic power consumption, even when it is in low data switching activity. Another type, SR latch-based one, also has some downside. Since it is a PMOS-based latch, it causes a longer setup time. Also, it has some power leakage problem when certain input and internal node combinations occur. Lin proposed a new low-power flip-flop design based on ACFF, which was SR latch-based flip-flop. The pull-down network, shown in figure 11, can go through transistor sharing by removing one redundant NMOS, which is controlled by CK. For the pull-up network in figure 12, one PMOS is shared between X2 and X2 bar to create virtual VDD. The complete block level schematic for the proposed design is shown in figure 10. This slide displays performance comparison with activity factor. In average, the proposed design showed 68% reduction in power consumption than the transmission gate flip-flop when tested with different data switching activity factors. Also, it achieved 63% reduction in setup time, which is smaller than that of AC flip-flop. Now it is time for conclusions. As I mentioned in the beginning of the presentation, the portable and wearable devices and IoT applications require low power integrated circuits to have longer battery life. The most power consuming components are the timing elements, which are mainly flip-flops and latches. The sequential circuits, which are critical for pipelining, are usually implemented using flip-flops. Therefore, it is critical to reduce power consumption on the flip-flops. I have presented 3 different ways to reduce power consumptions on the flip-flops. First one was to add 3 transistors to the basic dynamic flip-flop design, which resulted in reduction in leakage power consumption due to its noise robustness. Second one was to eliminate redundant clock transitions and transistors. After the 2 elimination processes, the new design showed significant power reduction while generating clock signal. Last design I explained was derived from the SR latch-based flip-flop. The design removes one NMOS transistor, which is shared, and one PMOS transistor to create virtual VDD. The new design showed some reduction in power consumption compared to the transmission gate flip-flop and SR latch-based flip-flop. Thank you for listening to my presentation. and here are my citations.